To review, the Bernoulli equation is that equation right there in the yellow box, and it deals with three types of energy-like quantities: pressure, gravitational potential energy, essentially, and kinetic energy, essentially. The height above a reference line, if the pipe is level, the h's are the same on each side. In this picture, you can see the h's are different, so those quantities will not simply cancel each other. So here's our problem. We've got a pipe that carries water under pressure in a factory. At one point, the speed is 2.46 meters per second, and the pressure is 31,500 pascals. In an adjacent section, the pipe is 1.75 meters lower. There, the pressure is 26,700 pascals. Find the speed in the adjacent section. So we're going to use the Bernoulli equation to help us solve this. But before we get to the numbers, let's make a prediction as to how the speed compares to the original speed. In other words, the speed in the section that we're asked about, how does that compare to the speed in the original section, 2.46 meters per second? And a good guess would be obtained by looking at the pressures. In the first section of the pipe, the pressure is 31,500 pascals. In the section of the pipe that we're asked about, the pressure is only 26,700 pascals. And according to the Bernoulli principle, when the pressure decreases, the speed must have increased. So we're going to predict that the answer that we get for our speed is larger than 2.46 meters per second. So I'm going to call the first section of the pipe section A and the second section of the pipe section B. And I'm just going to make a table here because I like tables. And these are the three bits of each quantity. So in section A, we're given that the speed of the water is 2.46 meters per second, which means that we can fill in this portion of the table. 1/2 times the density of water times the speed squared. We're also told that the pressure in that section is 31,500 pascals. So I'm going to put that in there. If we keep reading, it says, in an adjacent section, the pipe is 1.75 meters lower, which means that we need to decide on a reference line for the calculation related to gravitational potential energy. So, in section B, the pipe is lower down. So I'm going to call the elevation for pipe B to be h is equal to 0, which means the rho GH term for section B of the pipe is 0, which means that the h for section A of the pipe is 1.75 meters, because section A is 1.75 meters higher than section B, which means that rho times G times H for section A is that product. Then, if we go on further in the problem, it says that in section B the pressure is 26,700, and we are asked to find the speed in section B. So V2 is our unknown. We know 1/2 rho, and there's our V2 squared. So if we take these three quantities, 31,500, the product of those three numbers is 17,168. The product down here on the bottom, 1/2 times 1,000 times 2.46 squared, gives us 3,026. Similarly, on this side, we need the sum of these three quantities. 26,700, 0 obviously goes away, and 1/2 times 1,000 is 500 V2 squared. That sum must be equal to that sum. If we solve that for V2, which I trust you can do, we get 7.07 meters per second. Sure enough, we predicted faster than 2.46, and it definitely is.